Think about how you read a line of text. You don't read the first three words, stop, go back to the beginning, and read the first four words. Your eyes just glide forward, taking in new information while letting the old slip away. Computers, on the other hand, have to be explicitly told to do this. That instinctual gliding motion is exactly how the sliding window algorithm works. It is a technique used to process continuous blocks of data efficiently. But when first faced with a problem asking for a contiguous sequence in an array, the common trap is to write a nested loop. That creates a brute force approach that checks every possible combination from scratch. Look at this array of 5 numbers. If we want to check every block of 3, a brute force method starts at the beginning to read 2, 5, and 1. Then it completely resets. It shifts over one spot and reads 5, 1, and 8. It resets again to read 1, 8, and 3. This overlapping area is the problem. Every time the loop resets, it recalculates those middle elements. When dealing with thousands of data points, throwing away that previous work forces the CPU to burn cycles on data it already processed, turning a quick linear task into a slow O of n squared bottleneck. Here is the 5-step framework to fix that inefficiency by remembering previous states. Initialize, expand, check, contract, and update. We can test this blueprint on a classic interview problem, finding the longest substring without repeating characters. This diagram tracks our string and variables. We initialize our left and right pointers at index 0. As our right pointer evaluates the first letter, A, we expand our window to include it. We check that it's not a duplicate, update our tracking set, and record our maximum length as 1. Now we continue the expand phase. The right pointer moves to B and then C. Since these characters are unique, the window stretches, and our maximum length updates to 3. The next shift is where the logic takes over. The right pointer hits another A. We check our set and recognize a duplicate. Our window now contains a repeating character, triggering an invalid condition. Instead of restarting the whole search, we contract. The left pointer shifts forward one position, dropping the first A out of the window. The duplicate is gone, and the window is valid again. Because both pointers only ever move forward, we never erase our progress. Each letter is evaluated at most twice, once entering the window and once leaving, allowing the algorithm to process the entire string in exactly O of n linear time. This 5-step blueprint handles both string maximums and numerical minimums. This array shows positive integers. Our goal is to find the shortest continuous block that adds up to at least 7. We initialize our pointers at 0, track the current sum, and set our minimum length to infinity. Pause here and see if you can trace how the expand and contract steps will play out on these numbers. We expand the window by sliding the right pointer forward, adding 2, 3, 1, and 2. Our sum hits 8. This meets our target, so the window is valid. Now we contract to find a tighter fit. We advance the left pointer, dropping the initial 2. The sum falls to 6, which breaks our condition. We resume expanding, pulling in the 4 to bring our sum to 10. Then we contract again from the left, dropping the 3. Our new block holds 1, 2, and 4. The sum is exactly 7, and we've successfully shrunk our minimum length down to 3. By inching the bounds forward and refusing to look backward, the algorithm guarantees a linear time solution, regardless of whether you're stretching to find a maximum string or shrinking to find a minimum sum. This list outlines the specific signals to look out for. A problem will require a contiguous sequence. Ask for an optimization, like the longest or shortest subset, and specify a target condition to meet. When those 3 elements are present in a problem description, abandon the nested loops entirely and utilize the sliding window. Mastering data structures and algorithms comes from this kind of deliberate, pattern-based recognition. Once you learn to spot the underlying shapes of these problems, the actual code writes itself.